So thank you everyone for joining us today. My name's Catherine Lawrence and I work with the Science Gateways Community Institute in the community engagement and exchange area. And I'm just going to give you a few bits of information about this webinar and about the Science Gateways Community Institute, which sponsors this. In case you haven't joined us here before, we will appreciate it if you keep yourself muted. And if for some reason you become unmuted, we'll mute you for you on your behalf. You can also turn off your video if you like, and that both those controls are in the bottom right corner of your BlueJeans screen. Also, we encourage you to submit questions at any time using chat, and that chat button you can see near the top right of your screen, and I will be keeping an eye on those and sharing those with David and Stephen as appropriate. So also, in case you joined after the recording announcement, automated recording announcement happened, we're recording this and the slides will be posted online. So the Science Gateways Community Institute, just before we switch to the next slide, I just want to I want to let you know that our annual conference is coming up in just a couple of weeks. And so if you are thinking about coming, best to register right away because tomorrow is the last day for registering and today is the last day of our hotel block being held. So if you want the hotel deal, do that today. So carrying on, let's see if that will, oh, there we go. Okay. So just a few words about who we are, in case you're not familiar with the Science Gateways Community Institute. Essentially, we are here to build community among those who build the gateways, whether it's the technologies or that are behind the gateways or the gateways themselves, as well as the users of Science Gateways. We're funded by the National Science Foundation to provide these services to you, both online and in person, and those include a variety of services and resources from 5 different areas. The first area is an incubator, very much in the spirit of the startup incubators that you hear about in the high-tech industry. And essentially, we have an array of consultants who can provide short-term consulting to let you know about topics that might be very specific to gateways, and you may not be able to afford to hire someone with that kind of expertise. We also have a boot camp, which I'll talk a little bit more about in a moment, but that is a week-long intensive program to help gateways at any stage of their development to think more strategically about where they're going. Our second service area, extended developer support, provides direct custom development help, meaning you can have someone up to 25% for anywhere from 3 months to a year who can do development on your gateway. So these are experienced gateway developers who can then apply their talents to what needs you might have for your gateway, whether it's an area that you don't know how to implement, or if it's just you need some extra help to make your gateway happen quicker. The Scientific Software Collaborative has created a gateway catalog that currently lists more than 100 gateways and will also be including software components. So you can use that to promote your gateway as well as the components that you may provide and serve to others. BOINC today is a great example of the kind of software component that you can, you might want to promote in the catalog. Community engagement and exchange is where I am coming from, which is essentially we offer a bunch of different activities throughout the year, webinars on a monthly basis, and the conference once a year. But we also maintain our website and provide resources and other information on there. And finally, workforce development is good to know about if you have students who are interested in moving into the gateways field. There are special events and internships and workshops at conferences that have been developed by our workforce development program, as well as programs that are geared towards faculty who want to use gateways in their teaching. So if you have a gateway that you think would be appropriate for a faculty member to use to teach a particular topic, let us know and we'll promote it for you. As I mentioned, the boot camp, I just wanted to highlight this as a particular service area that we offer because we just finished our second boot camp last week. And essentially, it is 5 intensive days. We pay for all your food and the participation at the event. You pay your own hotel and travel, and you apply to participate in this. And generally, at 2 or 3 people attend from each project that is represented at the boot camp in order to brainstorm and work on how to do things around articulating the value of your gateway, identifying your audience, understanding how to how you fit in within the marketplace, and then looking at sustainability and promotion. So it's really interactive, and it's a great way to build community and find colleagues. And we have it as an intensive 1-week program specifically so that you can not be distracted by your daily routine and say, oh, I think I'll go listen to that webinar or something and not ever get around to it. So that's just a little bit about our boot camp. So keep your eyes out for when the next one will be happening, which will be in the spring. And finally, just a quick favor at the end of this webinar, we get our money from the NSF to provide this service to you. And the way we can demonstrate to the NSF that we're providing something of value is if you could give us some feedback. So our feedback form is actually 2 really quick questions plus a question asking if you have any other topics you'd like to hear about. So it is even less than 30 seconds. So we'll be providing that link in the chat at the end of this. So if you haven't, as I mentioned, if you have any questions, do put them in chat at any time during this presentation. So with that, I'm going to stop sharing my screen and let David put his screen up.
Okay, thank you, Catherine.
Thank you. And while he's getting his screen shared, I'll say, so David Anderson is the man behind BOINC, which he will explain what it stands for and so forth, but this is a resource that lets you use volunteer computing. So take it away, David.
Thanks for inviting me. I am a research scientist, I'm a computer science person. I work at UC Berkeley, and I've been working on volunteer computing for a long time now. I was one of the co-founders of Study at Home back in around 2000, and I've been developing BOINC since 2002. So I'm not sure if everybody's familiar with volunteer computing, but the idea is to use consumer resources, computing resources, to do scientific computing. The reason this is interesting is because there's a lot more consumer resources than organizational resources. Consumer products include conventional computers like desktops and laptops. These days, also mobile devices like phones can actually do quite a bit of, they have a lot of computing power. And essentially every consumer electronic product these days has a processor in it, and in theory, they could all do computing when they're not doing something else. There's a lot of consumer devices. So for example, if we look at conventional computers, there's about, let's say, 1 billion, it's actually closer to 2 billion. And with conservative estimates for their performance, we could get at least 1,000 exaflops. I think that's called a zetaflop. Realistically, of course, not everybody's going to participate, and these computers are not available all the time. But the number, if we can somehow publicize volunteer computing better, would be in the many exaflops. Smartphones have slower CPUs, but modern ones also have GPUs that can do in the range of about 300 or 400 gigaflops, and there's a lot more of those. So there's even more potential for computing in smartphones. We started BOINC in 2002 as an open source general purpose platform for volunteer computing. We wanted to make it possible for any scientist who needed a lot of high throughput computing power to set up a project. The software consists of two parts: the server that a scientist runs, which distributes their jobs and implements a website that tells people about the project, and the client part of the software is what you run on your computer or your smartphone, and you can attach your device to any or all of the projects that are running the server. The software deals with a number of issues that are specific to volunteer computing, in contrast with other forms of distributed computing. One is that the computation has to be invisible to the device owner. It can't slow down the performance of your computer, or run down the battery of your phone. We have to handle heterogeneity. The pool of these computing resources is as diverse as you can imagine. It includes all different kinds of operating systems, mostly Windows. It's about 85% Windows in the consumer space, but we need to handle Linux and Mac as well. And of course, there's many different versions of all these things, and many kinds of GPUs and different versions of their drivers and so forth. So the idea in BOINC is that a scientist submits a job not targeted at any specific platform, and BOINC makes the decision about, when it's sending the job to a client, which version of the application to use appropriate for that hardware. BOINC also deals with faults. There's potential for jobs to be computed incorrectly, or even for malicious users to try to cheat or gain credit for computing without actually doing the computing. So BOINC has mechanisms that use job replication in an efficient way to ensure the validity of results. This graph here is based on numbers from a few years ago, but I think the situation today is pretty much the same. If you want a lot of sustained computing throughput, you can get it by buying your own hardware, or renting hardware in the cloud, or using volunteer computing. And volunteer computing is a lot cheaper because all you have to do is maintain a server. What we're currently working on in the BOINC world is kind of a new way of organizing things, and this fits into the gateway idea. The original model for BOINC was based on the idea that individual scientists or research groups would create their own BOINC projects. We tried to make it really easy to set up the server and to port your applications. And the idea is that all these different projects would compete for volunteers by making websites that would explain their research and get people excited about what they were doing, talk about their credentials, and so forth. And on the flip side, the idea was that volunteers would kind of go around and look at all these websites, all these different projects, and make an informed decision based on their own priorities for what science they think is important, and contribute computing to those projects. And with the idea being that the projects doing the best science, or the science that appealed most to the public, would end up getting the most computing power. This model worked to some extent. There have been quite a number of projects using BOINC in a very diverse set of science areas. There's major projects doing global climate modeling, protein studies. There's Einstein at Home, which is looking for continuous gravitational waves, which have not yet been detected. CERN is using it to simulate particle collisions. They get more of their computing power from volunteer computing than they do from their own cluster these days. And there's, I would say, about 20 science projects using BOINC that are doing real science. The volunteer base consists of about 250,000 volunteers, most of whom have multiple devices. So there's about 500,000 active computers, a lot of cores. The computers average close to 8 cores, a lot of GPUs. And the total throughput currently is about 90 petaflops, which is would make it the most powerful supercomputer. It's kind of apples and oranges. So this model has some success, but it also seems to be fairly limited. The set of projects using volunteer computing is small, on the order of dozens, and it could. I was hoping that it would be hundreds or thousands. I think the reasons for this have to do with the model itself. Expecting a scientist to set up a BOINC project is probably unrealistic because it requires a lot of resources, a lot of technical skills that most non-computer scientists don't have. It requires the projects to publicize themselves, to try to, to make a nice-looking website or to get in the media or something like that. And that again is outside the domain of most scientists. It's also not really useful for projects that have a one-time burst of computing or a sporadic need for computing. And on the volunteer side, there's a fairly stable set of volunteers, but it's declining over time. It's definitely a narrow demographic. It's almost entirely male. It's almost entirely people with IT experience. And part of the issue here is that with all these projects, it's difficult to do marketing in a coherent way because essentially each project is its own brand. And the BOINC is not really a brand. It's just the name of the software. Trying to improve this model in a way that will bring volunteer computing to a lot more scientists, and we hope increase the volunteer base as well. The approach we're taking has 2 parts. One is to add volunteer computing backends to existing high-performance computing facilities, like supercomputer centers and like science gateways that offer computing. We're doing this in 2 places. There's 2 prototypes. One is at TAC, Texas Advanced Computing Center, which they do a lot of supercomputing, but they also do a lot of high throughput computing jobs that can run on cluster nodes or potentially consumer devices. The other prototype is at nanoHUB, and Steve Clark from nanoHUB is going to talk about those efforts after me. And the technical work we're doing will eventually become part of Hub 0 and will be usable for any gateway that uses Hub 0. So that's one part of the model. The second part is that there will now be kind of a central entity that I call the coordinator. Up until now, there's been no central component to volunteer computing. It's completely distributed. It's essentially it's anarchy. The idea of the coordinator is, first of all, it's a single interface that volunteers will see. So instead of having to go to dozens and dozens of project websites, there will be a single website that volunteers go to, and they will express their preferences for what kind of computing they want to do in terms of science goals. So you can go to this website when you're signing up and say, I want to do earth science research, or I want to do cancer research, there'll be a list of kind of science keywords. And then this coordinator will dynamically assign those devices, that computing power, to a potentially dynamic set of actual projects. And this is very important because it provides a way where a new project can get computing power without doing any publicity. It can essentially apply for an allocation to this coordinator and get computing immediately. In addition, this coordinator will act as a single brand for marketing purposes. I'm not exactly sure what the name of this is going to be. I need to. I'm actually talking with some marketing people in the business school here, but my personal favorite right now is Onboard. So I might call this Onboard the rest of this talk. Okay. So getting back to how you integrate volunteer computing with existing high throughput computing systems, there's a couple of parts to this. One is how to package your applications so that they'll run on home computers. Like I say, this really means Windows. Most people who do scientific computing develop on Linux, and there are some tools for cross-compiling from Linux to Windows, but they're tricky, and it's kind of a barrier to entry. So instead, we've been using a combination of virtualization technologies. The idea is that you'll just develop applications in your environment of choice, like Linux, and package them up together with a virtual machine for that environment and whatever libraries you need and whatever versions you need. And that virtual machine is what gets run on the volunteer computers. So we've been doing this for several years using VirtualBox, which is an open source hypervisor. CERN kind of pioneered this, and they're using this for all their volunteer computing. More recently, we started using something called Docker, which you can think of as being kind of a layer on top of VirtualBox that provides a nicer way for creating virtual machine images. It lets you structure the image as a set of layers that are separate files, so that when you're modifying something or releasing a new application, you only have to distribute a small file instead of the entire virtual machine image. It happened that the two partners, TAC and nanoHUB, were already using Docker, so this worked out nicely. The second part that you have to worry about is how you're going to get your input and output files from your current environment, whatever it happens to be, into the BOINC environment, and how you're going to transfer jobs from whatever your current queuing system is into the BOINC queuing system. So this is something we've been working on, and BOINC offers a set of web RPC interfaces for managing files and for submitting batches of jobs and getting the results of jobs. So we've developed interfaces for HT Condor. You can kind of plug in this adapter, and your Condor jobs automatically get routed to BOINC together with their files. We've also done it with the system that Hub Zero uses. Steve can talk about that. And at TAC, they use a system called Launcher, and our collaborator there has converted Launcher to be able to send jobs to BOINC. Yeah, so this is the way that this onboard thing works. And the idea is that the O represents a power on button. When you use onboard, you're powering up science in your computer. And like I say, the idea is that volunteers don't even see projects. So in the future, hopefully there'll be hundreds of projects doing all sorts of different kinds of areas of science. Volunteers won't have to learn about each one. They'll just pick the science areas they want. And the allocation will be done in a coordinated way using a model, a kind of a scientific merit model like Exceed. Of course, the volunteer preferences will have a large goal in which projects get computing. If if 90% of the volunteers say they only want to do cancer research, then those are the projects that are going to get computing, no matter how the allocation decision is made. The way things work architecturally, BOINC has this mechanism called the account manager architecture, where the idea is that instead of attaching your BOINC client to a specific project, you attach it to this account manager, and the client periodically does RPCs there, essentially asking it, which projects should I compute for now? So Onboard will kind of consist of two parts: a website, which is what the volunteers see, how they interface to it, and then an account manager that will make these decisions about which projects will be assigned to each computer. And this, of course, can change rapidly over time. So this part is the status of all this. We got funding for this about a year ago, and it'll run for a couple more years. The collaborators at TAC and nanoHUB have finished doing the application packaging part and the job submission and file management part. Both of these projects are shooting for a public launch in a couple of months. The public will be able to run nanoHUB jobs and TAC jobs. The work on Onboard is also mostly done, and I hope to have that launched by the end of this year too. So I'm here because I hope that other science gateways that need this particular kind of computing power will be interested in using the volunteer computing approach. By the kind of computing power, what I mean is, first of all, high throughput computing, meaning that your workload is not single jobs that have to get done quickly, but large numbers of jobs, like thousands or hundreds of thousands, where you care about the throughput rather than the latency of individual jobs. So on a gateway like nanoHUB, things like parameter sweeps, or Steve is going to talk about this in a minute. There's several use cases that generate large numbers of jobs where the low completion time is not really the target. It's high throughput. And in addition, these jobs should be fairly compute intensive. Roughly speaking, that means that they should do about an hour of computing per gigabyte of data transferred. Otherwise, you're going to spend all your time uploading and downloading files. So if you have a gateway that needs computing of this sort, and you don't have an infinite amount of money to pay Amazon, you should consider using this approach. And I'm interested in talking to you. There's my email address, and if you want to learn more about BOINC, there's the URL of the BOINC website. So that's about all I have to say. I could answer, if there's any questions, I could answer them, or we could move on to Steve's part of the presentation.
I think there is someone who would like to ask a question. John asked if we could pause for some questions, and I knew you were about to pause. So John, if you want to ask a question, you're welcome to unmute yourself as an option, or just put it in the chat section.
Yeah, I unmuted myself. Dave, you can hear me?
Yeah.
So this is John Towns. We've talked before on some of these things, but I had a couple of questions for you. One is you mentioned integrating into other high throughput environments, and could you comment on how well BOINC coexists with, say, HT Condor, and is there any real integration there, or do they sit side by side, or what does that look like if one were operating both a BOINC and an HT Condor services? What would the relationship be between them, and in particular, if they might be somehow sharing resources that jobs would run on?
The idea roughly is that the Condor scheduler makes a decision about whether it wants to process the job itself or hand it off to BOINC. That could be based on the current queue sizes on Condor's resources, and it could also be based on the characteristics of the job. Condor has a mechanism called the GAP protocol, GAHP, kind of a standard way to couple other batch systems into Condor. And a few years back, we did a collaboration with Condor to develop a kind of a BOINC module for that architecture, and it works really well. It's being used in a couple of places. CERN is using that. They use Condor for their basic job submission, and the sort of the overflow jobs go into their BOINC project.
So you could use a Condor submission interface and transparently make use of BOINC resources then, or the BOINC system.
Yeah, that's exactly what they're doing.
That's excellent to hear. I hadn't heard that previously. A separate question, your discussion about moving from projects to science goals as part of your challenges, and because I think most of the projects are transient, even if they're several years long, they eventually end. My question is, have you looked at other types of, say, long-lived activities that might not be aligned with a particular disciplinary goal? And my example here is, being at the University of Illinois, could we have a quote-unquote project that is University of Illinois that would support researchers who are at the University of Illinois in whatever they're doing? But this might be an interesting thing for, say, alumni of various universities to offer volunteer resources to support their alma mater, and those are long lived in that sense. Now, the presumption is that if they're coming from particularly a research university, there would be a fairly consistent overall load placed against the volunteers, as opposed to a project which might be either transient or sporadic.
Yeah, I think that would be a great idea. I didn't fully explain the keyword architecture. In addition to science keywords, there are also location keywords, like country, institution. So if volunteers, in addition to limiting the science areas they want to support, they can also say, I want to do only European computing, or only University of Illinois computing, or whatever. The resolution, so keywords are associated not just with projects but with individual jobs. So, for example, in the usage at TAC, they're going to use volunteer computing for many different things, biomedicine and physics, and so you can't associate keywords with the entire project, but you can associate them with jobs. So the same thing would work for a campus-wide project like what you described.
Excellent. Thank you.
Hi, Dave. I have a question. You mentioned the interest to tie into science gateways. I was wondering, is there currently a science gateway that's using your resources?
Yeah, nanoHUB.
Okay, and how does that look from a science gateway perspective? Like, what is it that needs to be integrated, or how does we need to change our workflow to use that?
I think Steve is gonna cover all that. So maybe we should move on to Steve.
Okay, thank you.
There are two questions that came in, and you can tell me if they're too long to answer now, or if you want to wait, or if you'd like to answer them now. One question was from Nancy, who's asking if how do developers typically prepare applications for this type of interruptible computing? Are there pointers we can provide to gateway developers?
Yeah. So one very nice thing about virtual machines, and in particular VirtualBox, is that they provide a efficient and generic way to do snapshots, to do checkpoint restart. In VirtualBox, you can sort of do a snapshot at any point in execution, and it doesn't snapshot the entire VM image. It just kind of creates a new diff file, and that whole thing is very efficient. So we can do that every, I don't know, three or 5 minutes, and that means you get restartability without fiddling with your apps at all.
Great. And then the other question was from Gary. He says, for users like myself of the current BOINC model, will the new coordinator-centric method replace the project-centric one, or will they coexist?
They'll coexist, and people who want to participate in a single project can do that exactly the way that they're doing it now.
Great. Well, so should we let Stephen jump on and he can talk about the nanoHUB approach?
Steve, you there?
Yeah. Oh, excuse me. Yeah.
So if you stop sharing your screen, then he can share his too, or he can boot you off.
No way. Oh, okay. Stop sharing. There we go.
Okay. Is it? You see my screen now?
I see blue. It looks like it's thinking, or maybe it just needs to be in a different location.
Okay.
I see your mouse too.
Okay. Well, that's not correct. How about now?
Yes. Yep. Got it now.
All
Awesome.
right, perfect. Okay. Good afternoon, everybody, or good morning. My name is Steve Clark. I work here at Purdue University in the Research Computing Department with specific areas of work in nanoHUB and hubzero.org. And today I'm going to speak to you a little bit about how we're integrating BOINC into the nanoHUB computational platform. And I've labeled this as re-enabling it because we've actually been doing this for 3 or 4 years, but this is a sort of a reboot of that whole effort. Oh, okay.
Sometimes you have to click on the slide and then do your arrow keys and it'll work.
Okay.
There you go.
You're right. All right. So I'll start with a little bit for those of you who may not know, what is nanoHUB and what do we do? nanoHUB is a website. In simple terms, it's been around for more than 10 years now. It's a place where scientists and engineers and researchers, students, and so forth congregate to do collaborative efforts. Once they're there, one of the features of the site is the ability to do simulation. And here I have a picture of many of the interfaces to some of the simulations that are available. Apologize for the fuzziness, but this photo has been, captured and removed and resized many times now. So other things they can do is just explore the area of nanotechnology and nanoscience. Hopefully they can learn something when they're there. There are courses available, university level courses, and many other resources. For simulation, which as I mentioned is one of the high feature points of nanoHUB or possibly any other Hub Zero instances, there are many use cases. The first one, and this has been around since the beginning, is that we provide an interactive environment that runs through your browser, where you can basically, there's some sort of interface, you declare all your inputs, you push a button and run a simulation. A few people, not everybody, but there are many people that have access to a workspace environment, which is basically a Linux desktop, and so you have access to a shell command line, and so you can do your usual building and development of applications, compile them, run them, and so forth, just like any other Unix type computer. And something new that's come along in the last year, maybe 2 years, we have a couple of GPU applications as well, and that's another one of the things that makes something like BOINC attractive. It will give us a platform maybe to run those. A second use case has to do with a caching system that we put together, where we find that we have about and there's on the order of about 500 different applications that people run, and most of the time people come in and to get familiar with the tool, the first thing they will do is run whatever the default case is, and so this case will be run thousands of times, and that's, in some sense, that's a waste of resource if we can just cache the result and immediately provide it when they hit the simulation button. And so, as you see outlined here, we have a mechanism in place to do that, and we have a backlog in the backlog cache. There's I'd say I don't have an exact number, but there's probably an order of thousands of, maybe tens of thousands of jobs waiting to be simulated, and this is a area ripe for something like BOINC to help us empty that queue, basically. Dave mentioned this case as well, parametric sweeps. This is available now through the standard submit infrastructure, which what we'll be talking about a little bit more here. The example here at the top is basically there's two variables, a VTH and a capacitance. Each one has a list of values, and the values here will be substituted into a file named indec, and then the simulator sim.exe will run all those different combinations. So here there'll be, well, I forget how many. But, so the first one there is a MATLAB notation. So there's 5 points between those two values, and there's 3 values. So probably 15 simulations that can be run with a single push of the button. This can be extended to any number of parameters, and there are many alternative ways of specifying that parameter list. Next on the list here is something else that's also available today, ability to do uncertainty quantification simulation. And the idea here is, if you remember from laboratory classes, you remember conducting experiments and trying to derive and fit error bars around your results. And this is along those lines, where inputs are never really fixed exact points. They have some sort of distribution or local to a point. So what uncertainty quantification does is allows you to specify those distributions and then run the simulation and produce outputs, which also now become distributions instead of fixed points. There's a whole there's a whole set of mathematics behind how to do this. And that is also integrated into the standard nanoHUB application structure. Another one maybe on the horizon is this ability to do maybe some sort of exploratory simulation where you just have something you want to study. You're studying maybe some sort of electronic device, and you have various parameters, sizes, thicknesses, whatever. And you may want to just, in an effort to learn more about a wider area of application, you may specify some boundary set, and you want to run some simulations within that boundary. And again, this can be run as basically a parameter sweep where you just list all the points you want to simulate. Okay, so that's the types of simulations we do, and now I'll speak to a little bit to how we do that today in sort of broad terms. So I mentioned we have about on the order of 500 different simulation tools, and on an annual basis we have from roughly about 15,000 people that will run at least one simulation. A lot of them will run more. A lot of them come in through classes. They stay with us for a semester, and then maybe they disappear. Maybe they come back. Researchers will run maybe different applications than students. So there's a whole spectrum here of demand and resource requirements. A great number of the jobs we can just run locally within a small set of nanoHUB servers. There's on the order of about a handful to half a dozen execution hosts that support all of the interactive sessions and can run a good number of the jobs, but certainly not all of them. The next tier of resource that's available, and this list is changed. It's a dynamic list over the last 10 or 12 years, and this extends out into what I've labeled here as HPC and HTC resources. So we've done the Condor thing with HTC, and we also have several clusters here on campus that we have access to. So those are the community clusters. Open Science Grid is another national infrastructure we take advantage of. Exceed is available. Red Cloud is a MATLAB enabled platform out of Cornell that we use for some distributed MATLAB computing. We've also had some experience, although not on any permanent basis, of connecting to cloud services like Amazon or Microsoft Azure. So the basic point there is that there's a whole wide variety of things that you might want to connect to that are suit your particular applications. Some applications run a single core in a matter of minutes. Some will take a whole rack of machines and take a week to run, and there's everything in between. All of those different resources have different batch scheduling systems, and there's a whole list of them pictured here. And then there's also typical and sort of standard protocols for exchanging data or data files back and forth, basically based on SSH. So submit is the command line. That's what you issue with the command. It's a sort of a wide extending infrastructure for executing any job on any resource outside of nanoHUB. It's entirely configurable through a set of data files that basically there's four major object types that have to be defined, and that's the sites, which would be which cluster am I running at, what's its address, what kind of a schedule is it running, things like that. There's the tools, and what we have to do here is define where are they located, where's the path to the executable, does it have inputs and so forth. There's an identity management piece because we're doing everything through community account mechanism. So Submit basically serves as a proxy to any remote resource or to map those 15,000 nanoHUB users into a community account. And then there's also the ability to restrict access to different applications based on who you are or groups that you belong to. To take a little bit closer look, a little deeper dive into this, for HPC, this is the current sort of setup here. So starting with the user in their web browser, they'll connect to the nanohub.org. Through some middleware, they'll be handed off to an execution host and attached to a VNC session. So that's what you see in your browser is a view onto a VNC session. On the execution host, we have, we have containers. They are OpenVZ containers, so they're very lightweight. They're process-based containers rather than virtual machine type environment. Within that container, you're going to run this particular tool, which is typically some sort of a binary, and there's some sort of a UI that sits on top of that, and maybe some interface between the two. If you need access to a remote site, you'll run the submit command, which is listed here as the client. It will connect over to a submit host, which is the server side, and it will distribute that job to the various resources that are available. Okay. In the case of a cluster, it'll land on a head node somewhere. The head node has many worker nodes. Important thing I want to say here is that we cannot directly necessarily transfer the nanoHUB tool binaries to the remote site. They typically have to be rebuilt. And there's a series of sort of 5 things that have to happen between the remote resource and the submit host, and those are listed here in the top corner. The different colors here on the diagram indicate shared drives. So within the hub, so the web host, the execution host, the submit host, is all shared drive space, so we don't have to ship files back and forth there. The remote cluster, of course, has its own different set of drives, and typically shared, at least some of them shared between the head node and the worker nodes. HTC is very similar. We do our submission to OSG, which is our major high throughput environment today, and we use there's a glide-in factory which uses pilot job technology in HC Condor to get access to nodes throughout the Open Science Grid environment, which is very large, very wide-ranging. And so now all of that, and for a couple reasons I'll go into here in a minute, we want to retain all of that, but add BOINC to the list, and hopefully do it in a way that's transparent to the end user or the application developer. So as Dave mentioned, we do this through the addition of a couple technologies. So the major one I pointed out here is Docker. We're making great use of that. In my representation, it runs inside the VirtualBox virtual machine container. You'll see there that there's something called the BOINC to Docker, which is that's the image that we use. I'll give you where you can look that up at the end of the presentation. And the major advantage of doing it in this way is that we can directly take the nanoHUB tool binary files and directly port them into the Docker container. We don't have to rebuild anything. So we can make the Docker environment match the OpenVZ environment by basically loading up the same package sets, the same Debian. As it happens, we're based on Debian system, but it could be anything. So between the server, BOINC server, which is actually separate from the submit server and has its own isolated hard drive and everything. So we need to ship input, basically application job specific inputs from submit host to the BOINC server, and then everything that is needed to execute the job needs to be transferred to the volunteer computer. And so here there's a list. The major ones here are the Docker files, which are the image star, and the layer star. The app star is say if I wanted to run lamps, there'll be a tar file that goes along with that. All of those files will be transferred. They remain on the volunteer computer. They don't need to be removed when the job is complete. The idea there being that you only have to upload them once and then you're good to go. The Docker container, I have used multiple containers. There's about 15 of them to support about 175 nanoHUB tools. And between them, there's a lot of overlap in the layer files that are shared. So it's not particularly high burden on the volunteer once they run the first job. Okay, so I've touched on all this. I think we're running a little low on time here, but basically the important point here again is that we can basically create a script that will bundle up the application you want to run, create a tar file of it, stage it on the BOINC server, and then you can use it in jobs. So that's this one, 15 files. There's a couple of utility functions to do this. Stage a Docker image and stage ordinary files. As Dave mentioned, there's a web RPC for doing the interface between the submit host and the BOINC host. And this is just an enumeration of what basically the names of the files are, but it breaks down into some very simple actions. And as I mentioned in the beginning, we wanted to do this without having to change our applications, and this has been accomplished mainly through use of Docker to mirror the local nanoHUB environment. So people either, if they were already submitting somewhere, they basically just now submit to BOINC instead of somewhere else. For a lot of tools that did not use submit or did not execute remotely before, they'll obviously have to add that, but that's a very simple process as well. Okay, so basically to wrap this up, here's a list of websites that provide probably useful information and serve as some of the background for the work that we've done here at nanoHUB. And as Dave mentioned, this is just coming online. It just went essentially publicly available yesterday. So if people want to sign up, you're welcome to download a BOINC client and a virtual box for your machine and go ahead and connect up to nanoHUB. And in the future, as is typical within Hub Zero, nanoHUB is the forerunner in all of this. And when we deem it to be stable and packageable, it will become available to other Hub Zero instances as well. And also, I should mention, I think both of us will be at the Gateways Conference in a couple weeks in Ann Arbor, so maybe we'll see some of you there. So that's what I have today.
Terrific. Thanks so much, Steve and David. I was just reflecting, I'm not a technical person, but you made it sound so easy. So I imagine it's a lot, not so much, but at least you're available to answer questions, and you pointed us to a lot of references. So thank you very much for preparing this, and congratulations on this hot off the press software. So
right.
That's awesome. I want to remind everyone who's on the call, it's 2:00 right now, or at least Eastern time. I wanted to remind you all that these slides will be posted online, so you'll be able to access all of these links and so forth from both of the presentations if you have any questions or you want to revisit any of this content. So with that, I'm going to just put this last slide up and share with you, just so you can find out from me what is coming up next month. Our next month's presentation I don't know why this. Oh, there we go. Is on usability, and it should be loads of fun. So, how to make your gateway easy and pleasant to use. It'll be an introduction to usability, user-centered design, offered by another person from Purdue, Paul Parsons, who is involved with our Science Gateways Community Institute and Incubator as well. So, please click through on the link as well to give us your feedback if you can take a moment to do that. But with that, I just want to again thank David and Steve for providing a terrific presentation about BOINC and letting everyone know how it's all put together and can be used in their gateways. So I guess we could stay on the line for a couple minutes for answering questions, but certainly no one's required to be on the call. So thank you all. Okay, no questions.
Thanks.
What's that, Nancy? Yeah?
I said I was thanking Steve and David for great presentations. I learned a lot. Steve, I was wondering what some of the biggest challenges were that you saw porting apps to this environment and how it worked for nanoHUB.
Well, the biggest challenge in all of this was new to me, so that presents a challenge. But I think we've gotten to the point now where it's very simple and we can almost automate it. And that's really the goal, is that the developers of the applications don't have to do anything different. We can take their application and just bundle it up and send it off. With the limitations that BOINC is not suitable for all applications, in the sense that if you need a big MPI job, you're not going to run it on BOINC. We'll continue to run those somewhere else. But hopefully this platform will make some more space on our otherwise crowded resources for those type of applications.
Right, yeah, great, because I know BOINC's a partner with the Gateways Institute, and we'd love to be able to advertise the resource more for gateway developers where the computing's appropriate, and yeah, terrific.
It would be good for us too. So.
Thanks for your question, Nancy. That's a good one. With that, I think we'll say goodbye, everyone. Have a great rest of your day.